Welcome to AI Paper Podcasts. Today we are doing a deep dive into the source material of a paper called Articraft.
Yeah, full title is Articraft, an agentic system for scalable articulated 3D asset generation.
Right, from researchers at Cambridge, Oxford, and NTU. And we're just jumping straight in today because this solves a massive bottleneck for physical AI.
Oh, absolutely. It's a huge step forward.
Because, for AI or robotics to actually understand the physical world, they need training data of objects that actually move.
Right, things like hinged doors, rolling wheels, sliding drawers.
Exactly. But existing 3D datasets are just tiny, and they are almost entirely rigid. So Articraft solves this by turning 3D generation into a coding problem.
Which is such a brilliant reframe.
It really is. It uses large language models, right, operating inside a restricted programming harness to iteratively write, compile, test, and fix Python code.
And that code generates highly detailed, simulation-ready 3D models.
Yeah, and they autonomously generated Articraft 10K with this. A massive data set of over 10,000 articulated objects spanning 245 categories.
And the craziest part is the cost.
Oh, yeah. It's about $1.13 per object, using only local CPU compute. It's a total game changer for training downstream models.
It really fundamentally changes how we construct training environments. I mean, to understand why turning an LLM into a 3D CAD engineer is such a big deal, we have to look at the data starvation in 3D vision right now.
Right, because we've gotten incredibly good at generating static 3D objects, but there is a massive gulf between a static mesh and an articulated one.
Oh, completely.
Like generating a static mesh is basically just taking a snapshot, but generating an articulated object is like building a mechanical watch.
I love that analogy.
Yeah, if the gears don't align, or the constraints are off, it's just completely useless to a physics simulator.
The mechanical watch analogy gets right to the heart of it, yeah. Because with a static object, the neural network only cares about the surface. But with articulated objects, the function depends on the hidden motion of the parts.
Right. You have to know what connects to what.
Exactly. The part hierarchy. And you have to define the joint types. Like, is it a revolute joint, like a door hinge? Or a prismatic joint, like a sliding drawer?
Or a continuous joint for a rolling wheel.
Yes. And on top of that, you have to define the exact physical ranges of motion in degrees or meters.
And historically, we've just forced humans to do this by hand.
Painstakingly by hand, yes.
I mean, I can only imagine how tedious it is to sit in Blender, manually highlighting vertices on a chair, setting up a joint axis, and testing the friction.
It is so slow, which is why we have this massive data scarcity. I mean, look at PartNet Mobility. It's arguably the standard data set right now, and it only covers 46 categories.
Wow, just 46.
Yeah. And newer ones like AKB48 or JPartNet, they rely on scanning real-world objects and then manually annotating them. So they're capped at a few thousand assets at best.
Which leads right into that classic machine learning trap, right?
Yeah.
Overfitting.
Exactly.
If you only have 2,000 models of 46 household objects, your AI just memorizes them. It learns those exact 46 doors. But then you drop it in a new room, ask it to open a microwave it's never seen, and it just fails.
It fails completely, which is why synthetic generation isn't just a nice-to-have, it's the only way to scale up for foundation models.
So we know we can't pay human engineers millions of dollars to manually annotate 10,000 objects. So the researchers used LLMs.
Yeah.
They didn't ask the LLM to spit out 3D coordinates. They asked it to write software.
Right. They built this domain-specific SDK software development kit based on CAD query.
Okay.
And the LLM is just tasked with writing one single Python file, model.cod.
Just one file.
Yep. The SDK exposes low-level primitives, like telling the system to draw a cylinder alongside high-level abstractions, like attaching a continuous joint. It makes the code really readable.
Wait, why go through a Python SDK? Why not just have the LLM output the raw URDF XML files directly? I mean, URDF is the industry standard for simulators.
That is the exact right question, and the researchers address this. It comes down to what language models are actually good at. URDF is basically this massive, deeply nested XML tree.
Right.
It relies on extremely precise floating point math for spatial coordinates, and it is so unforgiving with syntax.
Look, if you miss one closing tag, the whole thing crashes.
Exactly. And LLMs, despite how smart they seem, they're text engines. They're terrible at just blindly guessing raw 3D vertices in space.
Oh, okay.
But because they've been trained on massive amounts of code from places like GitHub, they are incredibly strong at writing modular Python code.
I see. So by wrapping it in a Python SDK, You're translating a spatial geometry problem into a logical semantic problem.
Precisely.
Instead of forcing the AI to guess the XYZ coordinates of a wheel, it just writes a function that says, create a wheel of radius 5 and attach it to the bottom left corner with a continuous joint.
Yes, exactly. It relies on its vast general knowledge of how everyday objects are structured and lets the SDK handle the back-end math to generate the XML.
Okay, let's unpack this. Even with Python, an LLM isn't going to perfectly simulate physics on the first try, right?
Right.
If it codes a moving forklift, it might still put the wheels inside the chassis.
Oh, definitely. It makes mistakes all the time.
So the iterative feedback loop is where it gets crazy. The system uses this agent harness.
Right, the harness.
I look at this harness like a combination of bowling bumpers and a compiler. If you just drop an LLM into a 3D software environment, it's going to throw a gutter ball.
Yeah, it gets distracted, hallucinating features.
Right. But the harness acts as these bumpers, keeping the AI strictly focused on the geometry.
The action space is highly restricted. The LLM can basically only do a few things. It can patch code, replace code, compile, run probes, or read the docs. When it compiles the code, the harness runs a bunch of sanity checks. It looks for floating parts that aren't physically connected, or invalid joint limits, or geometries crashing into each other.
And if it finds an error,
It intercepts the compilation and returns a highly structured error log back to the agent.
so it's literally a debugger, but for physical mechanics.
Yes.
So if the harness says error wheel is intersecting with door, what does the agent actually do?
It uses its probe tools. It can essentially query the spatial data, like give me the exact bounding box of the wheel and the door. It reads those coordinates, pinpoints the overlap, rewrites the Python code to shift the wheel over, and recompiles.
Wow. An autonomous loop of write, test, debug, and repair.
And they also integrated image conditioning.
Oh, right. So you can feed it a reference photograph and it uses it as ground truth.
Yeah, through a pipeline called Literality, which is super important for transferring from simulation to the real world. The asset doesn't just need to move right, it needs to look realistic to robot vision sensors.
So Literality pulls QBR materials from the image.
Exactly, physically based rendering materials.
So it's not just, grabbing a color hex code. PCR tells the simulator how rough a plastic is or how light scatters off a metallic base.
Right, so optical sensors in the simulation will perceive it exactly like the real photograph.
But there's a massive technical hurdle here. Anyone building agent loops knows that when an AI is iteratively debugging, the context window fills up incredibly fast.
Oh, token pressure is a huge issue.
Yeah, the taper notes that for long runs, the prompt token pressure hits around 272,000 tokens for GPT 5.5.
Which is right where you get context window collapse. The AI gets overwhelmed by all the past error logs, forgets the original goal, and just gets stuck in a loop.
So how does Articraft bypass that?
Through what they call context compaction.
Okay.
The harness monitors the token pressure. When it gets too high or the agent is just spinning its wheels, the system pauses. It takes the massive history of tool calls and compresses it into a concise JSON summary.
What actually gets compressed, though? Like, does it just delete the old code?
Sort of. It strips out the syntactic noise but keeps the semantic logic. So instead of thousands of lines of failed Python code, the summary just says, task is to build a chair. Attempt 4 failed because the backrest was disconnected. Attempt 5 failed because the joint angle was inverted.
Oh, wow.
Yeah, it preserves the reasoning trace without the raw code weight. The LLM reads the summary and just picks up right where it left off.
Which brings us to the economics of this. Because building a self-correcting agent loop that runs physical physics simulations sounds, it sounds insanely expensive.
You'd think so, yeah.
You'd assume generating 10,000 models would cost a fortune in cloud GPUs.
But the pipeline is incredibly lightweight. It runs entirely on local CPUs.
No GPUs at all.
No GPUs for generation. All the heavy lifting is just API calls to the LLMs.
And the cost breakdown is wild. It costs about $1.13 per retained object. If you hired a 3D artist to do this, you're talking hundreds of dollars per object.
And prompt caching is really the mechanism making that $1 price point work.
Prompt caching is the unsung hero of this paper. Like if you are building agentic workflows, this is the blueprint. They save so much, I think it was 85.7% of tokens were served from cache.
Right, because the agent isn't rereading the entire CAD query documentation on every single loop. The docs are cached, the base prompt is cached. You only pay for the net new reasoning tokens.
That 85% reduction is what makes generating 10,000 objects actually viable.
Absolutely. And speaking of the LLMs, they ran some great ablations. They tested GPT 5.5, Gemini 3.1 Pro, and Claude Opus 4.7.
All the heavy hitters.
Exactly. And all three could recover the basic structure, but GPT 5.5 really outperformed the others on geometric detail.
There was an amazing drone example in the paper.
Oh, yes.
They just turned up GPT 5.5's internal reasoning effort from low to high.
Yeah.
And simply by spending more tokens thinking about it, the number of visual parts it generated jumped from 39 to 78. It autonomously designed a much more complex drone.
But the real kicker is the user study. They had 125 participants do 5,000 blind comparisons against state-of-the-art generators like URDF Anything Plus and PhysX Anything.
Yet Articraft dominated. But what happens when you strip away the harness?
That's the best part. They tested raw GPT 5.5, no harness, no Python SDK, just asked it to write URDF files directly.
Yeah.
It ranked second to last.
Wait, really? Second to last?
Yeah. The raw intelligence of the model isn't enough. GPT 5.5 without the scaffolding performs terribly. The restricted Python SDK and that iterative bumper bowling feedback loop, that is the actual secret sauce.
By forcing it into the physical rules of a compiler, it literally can't hallucinate impossible shapes.
Exactly. The tooling unlocks the model.
So what does this all mean for you, the listener, if you're building physical AI? It means your baseline is shifted. Articraft 10K gives you over 10,000 assets across 245 categories, and it's highly curated with a 91.8% retention rate.
And we see the impact in the downstream tests. These assets import directly into NVIDIA Isaac Sim with zero friction.
Right, because they're compiled from code.
Exactly. Collision meshes, kinematics, everything just natively works. And they even retrained a vision model called Particulate.
Okay, Particulate is a feed-forward 3D articulation model, right? You feed it a point cloud, and it predicts the joints.
Yep. And when they trained it on Articraft 10K, the performance shot up. They tracked this with GIOU and MIOU.
Let's break those metrics down for a second.
Sure. So MIOU is mean intersection over union. Basically, if the AI predicts where a drawer is and you have the ground truth box of where it actually is, intersection over union measures how perfectly those boxes overlap.
Right.
I mean, IOU is just the average of that across all parts. And GIOU, generalized IOU, adds a penalty if the predicted box and actual box are super far apart.
It's a very strict accuracy measure, and those metrics jumped across the board.
But where they jumped is the most important part. The boosts were massive on out-of-distribution categories. Things like dishwashers, blenders, microwaves, things the AI hadn't seen in its original data.
Because it's not just memorizing 46 household items anymore. You gave it 10,000 diverse structures, so it learned the generalized concept of a hinge, not just a laptop hinge.
If we connect this to the bigger picture, we are watching the reality gap for embodied AI actively close. The human labor bottleneck for manually annotating physics is gone. The agent isn't just drawing shapes, it is mathematically defining the physical laws in executable code before the object even exists.
That is just a staggering shift. We spent this whole time talking about AI testing and debugging mechanical logic in a virtual space. But here's a thought for you to take away. If an AI agent can reliably code, compile, and test the structural integrity of a physical mechanism in a simulation and fix its own flaws, what happens when we remove the simulation?
Oh, wow.
Right. What happens when we plug these agentic systems into real-world automated manufacturing? Imagine a workflow where Articraft isn't outputting a virtual file, but compiling G-code and sending it straight to a 5-axis CNC machine or an industrial 3D printer on a factory floor.
That is entirely within reach.
We are rapidly approaching a world where AI doesn't just write our software, but autonomously codes, tests, and manufactures our physical reality.
It's incredible to think about.
Truly is. Well, thanks for tuning in to this deep dive on AI Paper Podcasts. We will see you next time.